Hey there, Calc folks, back here with what I hope is another quick lecture in our study of multivariable functions, where we are studying the application of partial derivatives here. And we have seen a few applications of the partial derivatives so far here. We've used them to perform some implicit differentiation. We've used them to calculate what we call the gradient of a multivariable function. And now what we're going to do is see how they are used to calculate what's known as the directional derivative. So I had noted back when I was introducing the partial derivative that when passing through a point on a surface, there's actually an infinite number of different directions we can pass through that coordinate. And I had mentioned that each of those different directions, when passing through that point, all yield a different instantaneous rate of change in the output of the function when compared to the change in the input. All right, when compared to the change in our domain. That change that could happen in any infinite direction passing through our point. And what we had noted for the partial derivatives is that those were the descriptions of change in the output of our function that would happen in one of two specific directions. The partial with respect to x was with respect to change in just x, where y was held constant, or with respect to y was just the change in z with respect to a change in x or y, where x was held constant. And I had noted that those were two specific cases of directional derivatives that would be used later on to calculate the derivative in any given direction. And now we're back to see how those partials are going to play a role in that calculation. And the way they play a role in that calculation is with their use in the gradient, folks. How we calculate a directional derivative will be with the gradient vector. All right. As noted in the section on partial derivatives, for z equal to f of x comma y, there exists an infinite number of rates of change in z at any location on the surface, pending the direction of approach. As noted, to calculate any one of these rates of change will require the use of partial derivatives for z of x comma y, the partial with respect to x and the partial with respect to y, respectively. All right. Now, the way this is going to be done is forming the dot product of the gradient being the del of f, right? The del operator applied to the multivariable function f. You're going to take its vector, the gradient vector, and dot it with the unit vector describing the directional change in the domain of f. This will produce a result known as a directional derivative that we see here given in the following definition. All right. You can see in this definition here, it does say for f, a function that contains itself in n-dimensional space. Right? For function f, I maybe should highlight that. For function f contained in n-dimensional space, the rate of change in function f with respect to a change in f's domain in the direction of the unit vector u, right? Where we might point out here that would be contained in the space that is the size of the dimensions of f's domain, which if f is in n, its domain will be in n minus 1, right? So that would be a unit vector in the domain described by the real number system raised to the n minus 1 power, and is given by this calculation seen here. Now, here's the notation. This is denoting what we call the directional derivative. We use the big D notation to highlight derivative. This is the derivative of function f in the direction of the unit vector u bar. And the way that that directional derivative is found is taking the dot product of what would be the gradient of f, the vector made up of its partial derivatives for our function f, dotted with u bar, where u bar is a unit vector describing the direction of change, right, in our domain of f, right? Let me even point that out here. The domain of f, right, is given by this directional derivative. Now, we can get specific to the case of three-dimensional space. For z equal to f of x comma y contained in 3 dimensions, the rate of change in z with respect to a change in x comma y contained in 2 dimensions, again, the domain of f in this case, is in the direction of the unit vector u1 comma u2, will be described by this calculation seen here. It will be the directional derivative for function f in the direction of u, denoted here, which will be equal to this dot product. It will be the dot product of the gradient of f of x comma y with that unit vector u. And in three-dimensional space, the gradient will be this two-dimensional vector made up of the partials of f with respect to x and y. And u will be simply that two-dimensional component vector, unit vector describing the direction with its components. All right. Taking the dot product of these two quantities will give you a calculation for the derivative in our function, multivariable function f, in the direction of unit vector u. Let's consider a calculation. Right. We might consider the surface f of x comma y equal to 4 minus x squared minus y squared. The directional derivative for this surface in the direction of the unit vector u bar equal to the vector 2 over the root 13 comma 3 over the root 13. Note, this is a vector that moves in the direction of 2 comma 3, but u always must be expressed as a unit vector. So in the direction of 2 comma 13, the magnitude of that vector is the square root of 4 plus 9, or the square root of 13 in value. So we divide by the magnitude, and that will make that direction vector 2 comma 3 into a unit vector in its description. So here we have our unit vector u bar. And what we're interested in finding is the directional derivative of f in the direction of u bar. All right? The directional derivative of 4 minus x squared minus y squared in the direction of that unit vector u bar. And what that is given by, folks, in definition, right, by definition, is this calculation seen right here. Let me bring that down just to highlight where these parts are coming from. Where the partials with respect to x and y are quick defined. The partial of this with respect to x is negative 2x. The partial of this with respect to y is negative 2y. And you're going to dot that vector with our unit vector, 2 over the root 13, 3 over the root 13. All right. Remember, dot product is first component times first component plus second component for a two-dimensional dot product, where we will produce these two terms in our final result. Simplifying that result, we can write the directional derivative as negative 4x minus 6y divided by the root of 13. This describes the derivative on the surface f in three-dimensional space at any xy coordinate. Just plug them into the calculation, x and y respectively, but in the very specific direction described by this unit vector. Right? The derivative on the surface f in the direction given by this unit vector at any xy coordinate will be described by this calculation seen here. So at x comma y equal to 1 comma 1 in that domain of f, the derivative of f in the direction of the unit vector is given by this calculation seen here. It is the derivative of f at 1 comma 1 in the direction of u, where we just go into the calculation seen above and plug in 1 and 1 for x and y respectively. In the numerator, you will end up with negative 10 over that square root of 13. And that is the rate of change in the output of this function with respect to a change in our input at the coordinate 1 comma 1 in the direction of this unit vector, where that unit vector says you're essentially moving 2 units to the right and 3 units up in direction. Well, what that rate of change tells us is that the function is decreasing because it's negative. It's decreasing instantaneously by 10 over the square root of 13 units. Right? Instantaneously. Root 13 is somewhere between, 3 and 4, so this is a number somewhere between 3 and 4 in value, 2 and 3, 3 and 4 in value. Right? Where if we actually note the illustration, we will see that negative behavior. Here's the illustration of this case, seen down below here. Here is our surface F. Here is our surface F. Here's the point at 1 comma 1 in our domain for x and y respectively. Notice orientation is a little funny. I just rotated it around so we could see it appropriately. See it as easy as we can here. We're at that location 1 comma 1. We are moving in the direction of this unit vector seen here in that domain. That is in the direction of 2 units in the positive direction for x, 3 units in the positive direction for y, but 1 unit in length in that description. So on our surface, at that corresponding location, if we were to move in this direction described in our domain by this unit vector, we would be moving along this path down our surface in this direction. And if we move along the path down our surface in that direction, you can definitely see that the surface is going, the z value of that surface is going to be decreasing. And we see that in this calculation. Right? As we move in this direction, at this value in the domain, on our surface, we are going to be moving down our surface on this path. And the rate of change in z would be negative in value. How much is our z value decreasing by when we move in this direction? Instantaneously, at that point, it's decreasing by 10 over the square root of 13 units. Instantaneously, when we move in that direction at that point on our surface. All right. That is a directional derivative calculation, folks. That's how we calculate the derivative at any point on our surface, in any of those infinite directions we could be passing through that point. We're going to make use of the gradient at that point on the surface and dot it with the direction of our change that's all being described down in our domain of the function. Right? If you take the gradient and you dot it with your directional change in 3 dimensions as we see here, or in any n-dimensional space as defined above, you will calculate the directional derivative of that function in that noted direction at any given coordinate on our surface, or as noted above on our hypersurface. All right. So that is directional derivative, folks. It's a quick little lecture here. It kind of takes gradient and just takes it a step further, where we're adding and building on top of our understanding of partials and their application. All right. So with that said, I'll stop this video here. Like I said, it's a short one, right around 15 minutes. And I will get this posted up to you folks. And we will be looking at wrapping up 15 very shortly. We got to look at tangent planes and we got to look at max and min problems. Those are 2 more applications of the partial that we're going to consider. All right. But I've been promising you this directional derivative stuff, right? Since we've been started talking about partials, this concept of directional derivative has been there. And here we are, folks. We just seen the notes over that. So, time to move on. So, tangent planes, max and min problems is where we're heading. And I'll have those notes up for you shortly. Hope you're hanging in there. Hope to see you in class in just a bit. And we'll continue our discussion then. See you though.